Hi, this is Beth Faber from the Hydrologic Engineering Center, and this is part two of the lecture on flood frequency guidance, Bulletin 17B and 17C. In our list of topics, we are on talking about missing values and zero flows and about low outliers and what we do with them. And we actually end up handling all of these things in the same way in some cases. So let's start with missing flows. So here's a gauged record for which the gauge was out of service between 1980 and 1988, right? So we've got this period of time here that we don't have any flow measurements. For Bulletin 17B, you had to ask the question, did anything of note happen in that period? But if the answer was no, then the period was treated the same way as any other ungauged period, perhaps before the gauge was in place, right? So that means that the record was just closed in on either side of the missing period, and the data for the years that were known is evaluated, right? So it's combined into a single record. In Bulletin 17B, we have some more options. That missing period, if we do know a little bit about it, such as we'd have seen a flow value of some value or higher, we can put in a perception threshold range of this threshold to infinity, and we'll end up using a flow range from 0 to that threshold to replace those values. Or if you'd like to handle it the same way as Bulletin 17B would have, and just say no, nothing at all is known about those years, then you just define the perception threshold range of infinity to infinity, and the complementary flow range would then be 0 to infinity, and therefore nothing known. And that would give the same result as the 17B computation. Okay, so let's talk about censored records, meaning flows that were above or below a recording level. So crest stage gauges are an example of a gauge that has a lower bound that can be measured. Their flows below that level can happen, and when flows are below that level, they're just recorded as a censored value. This is censored as an adjective, meaning we haven't done anything to the flow. It's just a flow that literally was too low to be measured and thus doesn't give us a value other than below the gauge level, right? Same thing can happen if there's an upper bound on what the gauge can measure, right? We can have a flow above the upper bound and therefore have a censored value on the high side. That's a little bit less common. Unobserved historical flows are also censored flows, meaning we don't know what happened, but they're within our record because maybe they happened since a big event that we do have information about. So censored flows are important because even though we don't know the flow value, we have to keep track of those years and the fact that something happened that maybe we can say some information about. Right, so let's talk for a moment about Bulletin 17B and the definition of outliers, right, which are defined as values that are notably different for the rest of the data, right? So Bulletin 17B had something called the Grubbs-Beck test, which was an outlier threshold, and it was used to set both a high and a low outlier threshold. And any values in the data set that were lower than the low outlier threshold were low outliers, and any values that were higher than the high outlier threshold were high outliers. And different things were done in either case, right? So low outliers were censored. And now I'm using the word censored as a verb, meaning we're taking a flow that was perhaps measured and we're saying, no, I'm not going to use its value, right? So the analysis excludes the value of those years, but not the fact that they occurred, right? 17B used something called the conditional probability adjustment. 17C uses intervals to represent that data. So the interval from 0 to some low value. Okay, high outliers aren't censored, and we are going to get to high outliers and historical data in the next video. So that is gray for the moment. So here's an example from a site in Oregon. This is 107 years of annual peak flow data. We have it sorted and plotted versus plotting positions. And then here is a log Pearson type 3 fit to these annual maximum flows. And the distribution doesn't fit well really anywhere, but the biggest problem is up here at the top. The top of the curve doesn't make sense. So the log Pearson type 3 distribution is a bounded distribution. And for negative skews, meaning a downwardly curved frequency curve, for negative skews, there's an upper bound. For positive skews, there's a lower bound. So here with our negatively skewed frequency curve, you can see it is asymptotically approaching an upper bound, which is going to be below the highest flow. And what that means is we're fitting a model that says that that highest flow isn't possible, right? That is not a good model to represent probability for this site. So we have to do something about this. So that's where the low outlier threshold comes into place, right? The Grubbs-Beck test gives a low outlier threshold at this level, which would have us define the low values as low outliers. And the Bulletin 17b uses something called the conditional probability adjustment that first estimated the frequency curve without those values, but then adjusted all the probabilities along the curve to reflect the fact that those low values actually were part of the data set. Right. So the result of that conditional probability adjustment gives a curve like this. There was a bit more room and probably a requirement that somebody doing a frequency analysis is going to study their data pretty closely. And I'm looking at these low values. I might say if these two are low outliers, this third one probably is too. Right? So if I were to go back to the low outlier threshold and override it, I might censor these three values, right? And here's the curve that I would get having censored all three. What's going to happen with 17C is it's going to use the multiple Grubbs-Beck test, and it's going to get a threshold that is notably higher and censoring all of these events as well. And with the expected moments algorithm fit, we get a curve that looks like this. A nice thing about this approach is that it gave a reasonable approximation on the first cut. The very first computation gives you a frequency curve that makes sense. Right? And it's important, especially if analyses are being done by local agencies that need the information, but maybe don't have a hydrologist on staff. So it's very important to get a reasonable answer on the first cut. Here's a different example, Oristimba Creek in Southern California. This example has been called pathological because it's a bit challenging for any approach. This is a location where sometimes the stream is dry for a year or more at a time, and so the annual maximums are zero. And for a log distribution where we're fitting parameters to the log of flow, and we have zero flows, the log is undefined, all right? So we can't actually do the procedure. So what I've shown here is that if we were doing a graphical frequency curve, zero flows don't really matter that much, right? The upper flows that aren't zero would be plotted against plotting positions, and the curve would be defined by the plotting positions, and so zero flows don't matter, right? But if we're not doing a graphical curve, the zeros are a problem. What Bulletin 17b does is it treats those zeros the same way it does low outliers, where it leaves them out, computes the curve without them, and then it adjusts the curve with a conditional probability adjustment, meaning adjusting the probabilities to account for the fact that those low values did happen. If the analyst went in and chose to specify another low value as a low outlier, it would give a curve that's a little bit less negatively skewed. If they chose to exclude even a few more points as low outliers, it would give a curve that is a little bit less skewed, but also has a lower standard deviation and comes out a little bit flatter, right? So now we have this solid curve. We're showing the first two as dash curves. So this might be your final result with doing a 17b analysis. Okay. The first thing that 17c is going to do is do that multiple Grubbs-Beck test and consider not just those values, but all of these as low outliers as well. It's going to replace those values with ranges and give us this curve as the first result, right? And again, this is a reasonable result from the first computation, which is a very important aspect of the new guidance. I'm going to look at one more example with low outliers. This is the Santa Cruz River. I believe this is an example that is in the Bulletin 17C examples. Here is it looks like about 1949 to 2014 data set of annual maximum flows. Here they are sorted and plotted versus plotting positions. And here is the original log Pearson type 3 estimate from Bulletin 17B. Right, so the Grubbs-Beck threshold did see one low outlier in this case, and this is the frequency curve that results from the conditional probability adjustment. And we have that same problem at the top, where the curve is obviously heading for an upper bound, and the highest two events aren't consistent with those upper bounds. This curve is saying that these two events can't happen, right? So if we were doing Bulletin 17B, we'd have to go in here and look at these additional low values. Now, looking at these additional low values, I might say that there really isn't a way that a single probability distribution can fit all of these annual maximum flows, right? We're doing a fairly simplified type of analysis, right? Where we're fitting one distribution to the annual max flow of every year. But the Annual max flow of every year doesn't necessarily result from the same hydrologic process. We're looking at a situation here where it's a different hydrologic process for the low flows than the high flows. So it's not really a stretch to say these don't belong in the data set. I'd rather evaluate the end of the curve that is kind of internally consistent, right? So I wouldn't feel that bad going in here and raising my low outlier threshold and leaving out a couple more points and getting a new frequency curve that does make some sense. So this is actually a pretty reasonable thing to do. I'm going to step through a little bit of the history of where the multiple Grubbs-Beck test came from. And for this example, if we were to use this new low outlier threshold and do the expected moments algorithm with it, we'd replace these years with an interval from 0 up to this level, and this is what the fitted frequency curve would look like from the expected moments algorithm. And we again get a frequency curve that's below the top values, and therefore it's a model that doesn't make sense, right? Because it's saying some of our observations are impossible. So this is the result that led to the multiple Grubbs-Beck test, right? So what's the problem here? Well, first of all, the presence of several low outliers can mask each other. They don't seem like low outliers if a couple of them happen, but they still might be low outliers in the sense that we care, which I'll get to in a moment. But the important thing was that the expected moments algorithm is more sensitive to the low values, and it tries a little bit harder to fit them than just the simple product moments without the iterative algorithm do. Right, so what's happening here is some values are having an unwarranted effect, was the phrase that we used, on the upper end of the frequency curve, right? But those values weren't identified by the Grubbs-Beck test. The multiple Grubbs-Beck test is a little bit more aggressive, and it's asking the question a little bit differently. The Grubbs-Beck test is based on seeking a single low outlier. It can identify more than one because it sets a threshold, and there might be more than one value below the threshold, and then you have more than one low outlier. But the multiple Grubbs-Beck test statistically is actually looking for more than one low outlier if such exists, right? So it's a more aggressive test. It identifies more values, and specifically it's trying to identify values that are potentially influential on the upper end of the curve. Now, I have to point out that no one on the work group for Bulletin 17C was aware of anything that rhymed with PILF, so we had no problem defining potentially influential low floods or low flows and calling them PILFs. Some others might have made a different decision. All right, so what happens with Bulletin 17C is it's going to recode these potentially influential low flows as censored observations, meaning an interval between 0 to the PILF threshold. Right. A little more information. These potentially influential low flows are values that have an inappropriately large impact on the upper end of the curve. And we don't want these lowest annual maximum flows to be driving the upper end of the frequency curve that is trying to represent much larger and less frequent annual maximum flows, right? So what that means is these flows have high leverage that we don't want them to have. So a PILF might be one of a few things. It might be an outlier in the sense that it's really a different physical process than the large events that we care more about. It might be a zero flow or an almost zero flow. It might be just an unusually small value given the rest of the sample, and it could be a regular small observation that just has a potential impact, right, upon the upper tail of the distribution. So let's look for a moment at leverage and influence. Leverage means high potential influence. And so if we look at these values here, we have a few values that are high. We've got this one low value that has a lot of leverage. But if we're interested in a linear model, it doesn't actually have a lot of influence on the resulting model that's fit than would have been fit without it. But if instead that value were higher, now it has the same amount of leverage, but now it has influence because now you get a different model with that value in place. So this is what's happening with the low outliers. They have both leverage and influence, and when they do have influence, we want to get them out of the way so we don't mess up the fit to the upper end of our distribution. Right? So this brings up the idea of robustness in frequency analysis. Robustness means doing a good job even when you're doing the wrong thing or in a difficult situation. So, as I mentioned, this is a fairly simplified analysis we're doing in fitting a single probability distribution to annual maximum flows, no matter how they happened. So, with that approach, an analytical distribution sometimes just can't really duplicate the true distribution of high flows in a watershed, especially when the record includes zeros and low flows and values from different flood processes. And in that situation, maybe we want to do a more complex analysis like mixed population. But for a Bulletin 17 approach, where we're trying to use this more straightforward process, sometimes it really just can't work. Right? Log Pearson type 3 isn't the truth. GEV and log normal are also not the truth. So what we need is robust procedures that give good estimates when we're doing the wrong thing, when the true physical process can't be captured by this single model, right? And so this robust procedure in this case was this multiple grub-spec test that censors a lot more of the values in the lower tail, right? So when there's some discomfort about how many low values are being censored, and if you feel that that's not the correct thing to do, this is kind of the reason in that we don't want to let the low values be influencing the upper end of the tail. So here is a higher low outlier threshold that takes two more of the values, and we're finally getting a fit with the expected moments algorithm that is a bit more reasonable. But then if we bring in the multiple grub-spec test, which was developed after this was noticed, then it censors all the way up to here and gets a frequency curve for the top that makes a lot more sense. Right. So again, this is the first cut analysis. It's going to give something that makes sense. And the reasoning behind censoring values that don't seem to be different from the rest is just that they have some leverage and influence, and removing them gives us a better fit to the part of the distribution that we care most about. So that is the end of the second video, and we're next going to be talking about historical information.